In this video, we will be looking at solving physics problems associated with pressure. Now, pressure is defined as the amount of force exerted per area, or pressure equals force divided by area. So to create a large amount of pressure, you could either exert a large force, or you could exert a force over a small area, or you could do both. Now, this definition also means that the units of pressure are newtons per square meter, which can also be called pascals. So we will either have newtons per meter squared or pascals as our units for pressure. And so one of the most important applications of a fluid is its pressure. And so let's see how we can use pressure to apply to a fluid problem. So here we have a problem to solve. We have a waterbed is 2 meters on a side and it's 30 centimeters deep. We're asked to solve for its weight, and we're asked to solve for the pressure. So part A, we need to find its weight if the density of water is 1,000 kilograms per meter cubed. In order to solve this, the first thing we need to do is we need to calculate the volume. Now, if we remember, volume is length times width times height, so we would have 2 times 2 times 0.3. Now, this is 0.3 because we need this to be in meters. You'll notice that we had the 2 in meters, so we're going to change this to meters. So 2 times 2 times 0.3, we get a volume of 1.2 meters cubed. We know that density equals mass divided by volume. We need to calculate the mass. So we have a density of 1,000 kilograms per meter cubed equals our mass, which is our unknown, over our volume of 1.2 meters cubed. And we solve for mass, we get a mass of 1,200 kilograms. To calculate the weight, weight equals mass times the acceleration due to gravity, which would be our 1,200 times 9.8, and we get our weight as 11,760 newtons. Next, we're asked to find the pressure that the waterbed exerts on the floor, assuming that the entire lower surface of the bed makes contact with the floor. Pressure equals force divided by area. However, we are not given the force. We can substitute in mass times acceleration due to gravity for our force, and we calculated that right here. So we can plug that number in. Our area is our length times our width, so we're going to multiply 2 times 2, and that's where we get our 4 meters squared. And so we get the pressure as being 2,940 Newton meters squared. Now we know that a solid surface can exert pressure, but fluids such as liquids and gases can also exert pressure. And so if a fluid is at rest in a container, all the portions of the fluid must be in static equilibrium. In other words, all the points at the same depth must be at the same pressure. And so the fluid would otherwise not be in equilibrium. And so we can see variations of pressure with depth. The fluid would flow from the higher pressure region to the lower pressure region. So that the equation for pressure and depth is that pressure equals the PO is the normal atmospheric pressure, and that's going to be 1.013 times 10 to the 5th pascals, or 14.7 pounds per inch squared, plus our density times our acceleration due to gravity times the height. And so the pressure does not depend upon the shape of a container, but rather these components. So that a closer look, we would see our absolute pressure would equal our initial pressure, and this may or may not be in atmospheric pressures, plus our density times our acceleration due to gravity times the depth below the surface. And here when we see the change in pressure, this can be a gauge pressure. So this is the change in pressure, or the difference between the initial and the absolute pressure. So here we have an example problem to solve. We need to calculate the absolute pressure at an ocean depth of 1,000 meters, assuming that the density of water is 1,000 kilograms per meter cubed and the initial pressure is 1.01 times 10 to the fifth pascals or Newton meter squared. We have our formula here where we have our absolute pressure equals our initial pressure plus our density times the acceleration due to gravity times our height. Right here we have our initial pressure as 1.01 times 10 to the fifth pascals, and we got that right here. Plus, we have our density of water is 1,000 kilograms per meter cubed. The acceleration due to gravity is 9.8, and we see that the depth of the water is right here as 1,000 meters. We put that in here, we solve, and we get 9.9 times 10 to the 6 Newton meters squared as our absolute pressure. Now this could also be written as 9.9 times 10 to the 6 pascals. The second part of the problem asks us to calculate the total force exerted on the outside of a 30.0 centimeter diameter circular submarine window at this depth. So we know that pressure equals force divided by area. Force is our unknown. Our area is pi radius squared. Now we just calculated our pressure. So we can say our pressure 9.9 times 10 to the 6 equals our force, which is our unknown, divided by pi 0.30 squared. And so when we solve for our problem, we solve for force, we will get 2.80 times 10 to the 6 newtons.